Hello, hello, Vic again. Hello. And I got the thing, Vicky. Yeah, okay. I got the, yeah, okay. Hello,
Good
Lear.
afternoon, Professor.
Good afternoon. Good afternoon. Uh, oh, a lot of people. Okay. And good afternoon, Victoria. And good afternoon, Bridget. And good afternoon, Joel. And good afternoon, Anthony. Oh, that's a new, I think. And good afternoon, Gabriel. Good afternoon, Kian. Sorry. Good afternoon, Vicky for the double. Good afternoon, Mafine. Good afternoon, Victoria for the double. Good afternoon, Roger. Good afternoon, Abid. Good afternoon, Joel for the double. Sorry, and I did say hello to Joel. I did. Anyway, good afternoon, Caitlin with the exclamation point. Double enthusiasm. Good afternoon, Zoe. Good afternoon, Keon for the double. There are people in the waiting room. I apologize. Okay. Uh,
Good afternoon, Professor.
Who's oh, good afternoon. Good afternoon, Mohammed. Thank you. Good afternoon. I love it. And I've just lost my good afternoon, Gabriel for the double. Raina, good afternoon. Hello, Anthony for the double for the avatar, which that is not One Piece, is it? No, no, no. Okay. Sorry. Is that offensive? I just said that. Um, hello, Ant. I said that. Good afternoon, Melanie. Good afternoon. Good afternoon, Lachman. Good afternoon. Yes. Good. Okay. 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 And anybody I didn't say, Fabia. Good afternoon. Okay, let's just get rolling. He always says that. Again, still, some of you have gotten exams like some of you have not. I'm still working on it. I apologize. It's not personal. I think you know. I'm just going to keep rolling, but you will all get them. Um, and we will talk about them before the final or what to do for the final before the final. Yes, and good afternoon, Lachman. Or did I say that? Okay. So let's get back to the material. Uh okay. Today, is that what I mean to say? Yes, yes. And obviously stop me at any time with questions or whatever. Okay. I want to wait, something. Give me a second. Sorry, things happening. Oh, okay. One second. I'm sorry. Direct chat. I'm sorry. Okay. 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 What I want to continue with the material. If there's anything else in the chat, wait, am I seeing the chat? I mean, I am seeing the chat, but am I seeing it Okay, okay. Um, I want to continue the material from Monday. Here, and it's going to be of a different flavor today. Like, okay, the larger topic here, well, the larger topic is electrostatic fields. The subtopic is electrostatic fields due to continuous charge distributions. The central point that we are considering sort of for the rest of the semester is given a bunch of charge over here, what is the electrostatic field at a point in space over there? Right? Like that's literally like the central question of the study of classical electrostatics. Given a bunch of charge over here, what is the field over there? And when I say what is the field, I don't really mean what is a number. I mean what is a function, right? We're trying to figure out if you have a bunch of charge over here, what's the pattern of the field doing? Like if you we figure out the pattern enough, the function enough, that if you named any arbitrary point in space, we could tell you for that arbitrary point in space what the vector is doing, how long it is, and what direction it's pointing in. And right, that's like our ultimate goal here. And we want to be able to do it for like realistic macroscopic arrangements of charge, like not just a dot or even three dots. We want to be able to compute field due to a line of charge, as in a wire, or a plate of charge, as in a capacitor, or a ball of charge, as in a Van de Graaff generator or something like that. Okay. So the idea is you've got these big arrangements of net electric charge somewhere, and we want to know what is the resulting field function in all the nearby space. So, what Monday we were saying, in order to do that, we still believe that at every single point in space, there is a vector that represents the magnitude and direction of the electrostatic field at that point. Like we still believe that. But now, in order to get the larger pattern of all of these vectors in some region of space, in our minds, we've sewn up all the vectors and we imagine these lines called field lines, right? The field lines give all the same information as the vectors do, but in a more efficient way. The field lines capture the larger picture and pattern of what the field is doing, what the magnitude and direction of the field is doing throughout a region of space. So Monday was very visual. Monday was very visual. We were like examining the rules for writing and reading these field line diagrams that capture the information I just described. Now, Wednesday, I mean today, still looking at the same context, still the same issue, which is what is the field at a point in space due to some continuous charge distribution elsewhere in space? Same issue, but now we want to get mathematical about it, which will be a relief to some of you, I'm sure, and annoying to others of you, I would imagine. We're going to get mathematical now. I'm going to introduce something called flux, electrostatic flux. It is the concept that is needed for this last homework that is due next week, right? Yeah, I'm not going to do the whole homework today, but I'm going to start you on like the concepts of the homework today. Um, so the concept is flux, electrostatic flux. And the definition of electrostatic flux is that right there in the center of the page is a double integral of a dot product. Now, so in some ways, lecture over. That's what flux is. Thank you very much. But no, of course, not only is it my job to show you some applications and examples of how to compute flux and to show you the usefulness, like why we care about flux in the first place. I mean, I have to show you all that. But even before we do all that, I have to unpack exactly what this definition means. I mean, it's obviously a mathematical definition. So I'm going to spend a considerable amount of time today analyzing for you or trying to present to you um, what is meant by this mathematical equation, what is meant by this definition, and why it's stated the way it's stated. So the point here is electrostatic flux. And the point is to break down this equation. So wait, sorry. I'm looking at the chat. Yes, technical issue. Got it. No problem. I hear you. Okay, so I'm gonna. Okay. Flux. So I'm gonna be English first. I'm gonna try to explain the English and then bring it back to the math. In English, flux means flow. Well, I mean, in Latin, the word flux means flow. So in physics, whenever we talk about some kind of flux, whether it's electrostatic flux or magnetic flux or wind flux or water flux, when we say flux, we mean flow, but we specifically mean flow through a space as not as opposed to flow through a time. Okay. We don't mean flow like a river right now. We don't mean anything's dynamic or changing in time. What we mean is stuff is passing through an area. That's what we mean by flux in the broadest terms. Okay. But now let me be more specific. Okay. So flux is stuff going through an area. For example, again, it could apply to anything. Ultimately, we're going to apply it to electrostatic field, but the concept of flux is like you could have water, you could have rain flux on the roof of your house, and the more rain you have hitting the slab, the area of the roof of your house, the more flux we would say you have. Now, so flux really consists of two ideas: the stuff that's flowing and the area that it's flowing into or out of or through. Okay. And when I say area, I specifically mean like two-dimensional space, two-dimensional region of space, as opposed to volume or something like that. I really mean area. Always. But I also want to make clear before I get back to the math, well, to transition to the math, I want to make clear that the concept of flux is a product. It's not a quotient. So flux in broad terms is stuff times area, meaning meaning if you had more rain hitting a given roof, you would say that's more water flux. But also, if you had the same amount of rain hitting a bigger roof, we would also say that's more flux. Flux is a product. So if either one or both gets bigger, the whole total gets bigger. So that may be a little, but that's the case. Okay. Um, so that's the next piece. Uh, Finally, when we say through, when I say flux is like flowing through an area, By through, what I mean is perpendicularity. So, so if we were talking about the rain example, if you had a whole bunch of rain hitting the roof, perpendicular to the roof, that would be a whole bunch of flux. You could have the biggest roof in the world and you could have as much water as you possibly like. But if the water's trickling along or even flooding along the roof, if the water is moving, if the water is hitting the roof parallel to the roof, that's not flux at all. For it to be flux, there has to be a component of stuff that is perpendicular to the area that the stuff is hitting or passing through. So the rain could be hitting the roof on an angle. Like you could have rain falling like this and a roof like that. You could have that at an angle. And then what you would do, and so then that would be some flux. It wouldn't be as much flux as if it were like this, but it would be some flux. How much flux would it be? Well, you're a physicist. You know, you would take the direction of the rain and you would divide it into two components. One component that's perpendicular to the roof and one component that's parallel to the roof. And whatever component is perpendicular to the roof is all of what you would count as the flux. So it would be like the cosine or the sine component of the rain would be the flux, right? So I'm just trying to build the math here. I'm saying that what flux is stuff times area, but only along the axis that is perpendicular to the area. That's what we mean by flux in general. Now let's apply it to electrostatic fields. One second. Okay, sorry. All right, so I want you to consider a small. I said finite. I'm sorry. Hold on a second. Not even listening to my own class. Okay. Consider a small but finite bit of area. So delta S. Remember, delta is what we use when we're talking about small but finite differences in the value of a variable. And S, I'm going to use S stands for surface here. So you have a small but finite bit of area, like a delta X times a delta Y. Okay. And we're going to consider the E field. When we're talking about electrostatic flux, we're going to be talking about E field lines passing through this area. Well, it's going to, so in general, the more E field lines we have hitting this area, the more electrostatic flux we're going to say we have. And or the bigger this area is for a given amount of E field lines, the bigger the flux we're going to say there is. But the angle matters, right? I mean, because of what I said a second ago. Like, if we had a bunch of E field lines hitting this area like this, we would say we have a lot of flux. If we have a bunch of E field lines just grazing the area, passing over it parallel, then that's not flux at all. If the E field lines are in the arbitrary case of hitting the area at some angle, then we're going to have to take components and say, that a component of each E field line is constituting flux. So that means we've got to be tracking the orientation of this area. Like it matters, if the area twists, then that's going to change the angle. So the way we do that is in our minds, we attach a vector to the area. Like in our minds, we stick a little flag on this area and we make that so it's not a flag, it's an arrow. We stick an arrow out of the area at precisely 90 degrees to the area. We make an arrow that's normal, like remember, normal in math means perpendicular. We make an arrow that's norm to the area. Uh, and it's there to indicate direction. It's a unit vector. It has a size of one, but it's there to indicate the direction of the area. So from now on, if that area twists, then the arrow will twist and always by the same amount. So if the area twists by 90 degrees, the arrow will twist by 90 degrees. So this is a slightly confusing. So we're sticking an arrow to the area in our minds so that now we can treat the area as a vector. I mean, area is not actually a vector. Area is a two-dimensional concept, not a one-dimensional concept, right? But we care so much about the orientation of the area that we're attaching a vector to it and then using that vector to identify the whole area in a vector kind of way. Okay, so in other words, from now on, then if I say the vector delta S, if I say the vector delta S, I mean the vector whose magnitude, whose size is the area of that slab, and whose direction is the direction perfectly normal to that slab. Okay? So now there's a vector that represents area in my mind. The one thing I have to emphasize before I move on, and the reason again I'm turning area into a vector in my mind, and the reason I'm doing that is because I'm going to have to measure the relation, the angle between that area and any E field lines that are coming in if I want to measure flux. The one thing that you have to like catch before I move on is that if I say the area is pointing up, right, that means the arrow is pointing up. So that means the area is actually horizontal. If I say the area vector is pointing to the right, it means the area is actually vertical, right? Wherever the direction of the area is actually always perpendicular to what the area looks like, right? Because that's like just the easiest way to do it. Okay. Under that definition, This is a little bit subtle. So just trying to get this legible. Just it's not legible. That's supposed to be a theta there. All right. So I'm trying to say that a little bit of flux, like I'm trying to define what a little bit of electrostatic flux would mean. A little bit, a small but finite amount of electrostatic flux would mean the amount of electric field that hits an area, but perpendicular to that area, right? So the way we would write it mathematically, it would be the dot product of E field times area, the dot product. I'm being redundant. The dot product. Remember that the dot product measures parallelism. Remember the two key things about the dot product. One, it measures parallelism between two vectors. Two, it multiplies the two vectors and then produces a scalar answer, right? The dot product is the measurement of two vectors, is the scalar measurement of the extent to which two vectors are aligned with each other, right? Like work was the dot product of force and displacement. So I'm saying if we define area this way, hold on. Oh, very good. Wow. Awesome in the chat. I'm seeing in the chat. Yes. Right. No, I totally get it. Let me, no, that's perfect. Let me just see, make a decision of how. Well, okay, I'm going to say, yeah. I'm going to read that. I'm not going to read the person's name, but this is awesome, and you should definitely submit for points. So someone's saying in the chat, hello, I'm sure the concepts are kind of different, but when I was doing the assignment, homework 7, which is what we're on now, that's good. I ended up with this type of relationship, the type that I have on the board. I'm not exactly sure, but it seems to be similar to how work functions for force. And because I remember I used this justification in order to transition into an integral. That's fantastic. I'm not, that's exactly what I'm doing. You're totally right, person in direct chat. Let me say to everybody, yes, anything that you might have remembered about how we moved from force to work, we had to take 2 steps to move from force to work. We had to get our minds around the dot product and we had to get our minds around integrals. That's exact. And one of the reasons I made a big deal of that at the beginning of the semester is exactly this, that this is a more abstract version of the same thing or of a similar thing. That first of all, we're doing a dot product here. Yes, we're doing a dot product because we want to multiply two vectors together and get a scalar. Flux is a scalar concept. Flux is a scalar concept. Wait. Yeah. Yeah. 100% person in the direct chat. Same person. Yes. Awesome. So I'm going to say this to everybody now. The first thing I'm just addressing right now is the dot product, but there is a subtle, like, yes, if you understood this with work equals dot product of force times displacement. Like hold that in your mind because I'm doing the same thing here. But there's a twist here. Like that's why we do that one first. There's a twist here. I'm saying that a little bit of flux is an E field dotted with a little bit of area. Dotted means you take the two vectors and you multiply the cosine component of one vector times the other vector. In other words, the more parallel they are, the bigger product you'll get. Now, let me say to everybody, that might be slightly confused. And that's what we do with work. Like the more that you are pushing the block in a direction that is aligned with the block's motion, the more work you're doing on the block, the more energy you're transferring to it, right? dot product is all about alignment, parallelism. And we are using a dot product here. And we're using it, we're using a dot product here. But you have to pay attention with me because the two vectors that are being dotted are the E field line vectors, the blue ones, or any individual one, is being dotted with the area vector. So we're looking at how parallel the E field line is with the area vector. And the more parallel they are, like the bigger the cosine is, the more parallel they are, the bigger the flux product we're going to get. But the area vector itself is perpendicular to the actual physical orientation of the area. So by measuring the dot product with that norm vector, by measuring parallelism to that norm vector, what we're actually doing is measuring perpendicularity to the whole slab. I want everybody to understand. Anybody who just heard that, just put in the direct chat, like anything. If you just heard me, if you're okay, like I'm trying to say, flux is about perpendicularity, but we're using a dot product, but it works. We're using a dot product to measure perpendicularity because we're measuring a dot product between field and a norm vector. Understood. Okay. One person says understood. That's good. I'm going to wait till there's two people. All right. Good enough for me. Great. Great. Yeah. Oh, that's fair. Someone said a little confusing, but I'm getting there. That's totally fair. Totally honest. I appreciate it. Okay. Awesome. Yes, it is a little, and it's not the last time I'll ever say it, but yeah, I'm saying we care about perpendicularity. Flux is about how much stuff is flowing through. But we're going to measure that using a dot product, which is a little bit surprising because dot products we usually use for parallelism. But what we're measuring here technically is a line that is already perpendicular to the area. So we are ultimately measuring perpendicularity. And you might say, okay, I get it, but like, why do you physicists have to be such jerks? Like, why do you have to do that? Well, there's two reasons. Okay. Number one, the main reason is because we need it to be a dot product. We could have used the cross product or something, but then the cross product's a lot harder, honestly, than the dot product. We try to use a dot product when we can. And partly it's that the dot product produces a scalar, like work is the scalar product of force and displacement. This is the person in direct chat who compared this to work is like, it's right on the money. This is very much like the concept of work for reasons you're going to see in a couple of minutes. So we're trying to model after that. And we need the result to be a scalar. So we're using the dot product. And then finally, also, even though it's a bit confusing at first, even if you were inventing this on a desert island, frankly, you would try a couple other things first, as I'm sure Gauss and other people did. But you'd eventually arrive at this conclusion because once you're looking at the orientation of an area, you have to use an arrow somehow. Arrow is how we use direction. I mean, is how we track direction. And ultimately, the easiest place to put the arrow is just sticking out of the area. Once you play around, you'll realize like having any because the area might go on forever. Like where are you going to put the arrow? Like, okay. So anyway, so a little bit of flux, a small but finite amount of flux is small but finite amount of is field times small but finite amount of area, but times in this dot product way so that we only get the proper components. Okay, that's a small amount of flux. Now, I'm saying color, but so this is what we have so far. A small but finite amount of flux. Oh, yeah. Totally. Person in direct chat. I recognize this from calculus. Plane equations are defined by. Yeah, I mean, it turns out I'm making a big deal of this because it's like the first time that many of us are seeing it. But right, it's totally a tradition for good reason. It's totally a custom across the board to track the direction of an area by using an arrow that is normal to the area. Right. That actually just turns out to be universally convenient. Yes, totally good person in direct chat. Um, that's a different person, by the way. So at least two people in this class, actually, at least four people in this class are totally with me. Okay. Anyway, so that's a small amount of flux. So then, as a couple people in the chat are indicating, that's a small amount of flux. Right? That would be just how much flux is going through some small amount of area. And then you might, this is again, just like we talked about with work, you might say, well, what do you mean by a small area? Like how small? And why are you even restricting yourself to small? By small area, in this context, I mean small enough that the E field pattern doesn't have room to change. But I, that's what I mean by small. A small amount, an area that is small, sufficiently small to prevent variation in the field pattern. If you want the flux through a large area consisting of a bunch of tiles, what you could do would be to take the flux in each tile, like multiply the field times the area of the tile, put it in a bag, and then walk to the next tile, do that product, put it in your bag, then walk to the next tile, et cetera, and walk around the whole thing. And that would get you the total amount of flux, right? And that would allow you to get the total amount of flux, even if in each tile there was somehow a different pattern of field lines. Like if the field line distribution were varying throughout those tiles, if you just went tile by tile by tile and added them all up, you would have the total flux. But if the field pattern was changing continuously, if in other words, no matter how small you made your tiles, you still couldn't grab a constant amount, like that it was just changing smoothly throughout the whole thing, then you'd have to make your tiles infinitely small in order to account for the sum of all of those products, right? And that's what an integral is, right? In other words, what I'm saying, and again, I'm proud. I'm really happy that one of the direct chat people like totally anticipated this about 5 minutes ago. It's great. Like I'm saying, a small but finite amount of area produces a small but finite amount of flux. The flux is the field dotted with the area. Then, if you want flux in general for a full area, what you have to do is go bit of area by bit of area, multiplying for each bit of area and adding up all those areas. If you take that to the limit for which each area is infinitely small, in order to account for continuous changes, then taking that sum of products to the limit is called taking an integral. In this case, it happens to be designated in many textbooks and websites will be designated with a double integral. Don't let that intimidate you. You may never have seen one before. It's fine. It's a double integral just because it's two-dimensional, because the variable of integration now is S for surface. So technically what this really is an integral across dx times an integral across dy. Like you can really think of it really is two integrals, a length integral and then a width integral if you like. But if we're thinking of it all at once, if we're thinking of it as stepping from tile to tile to tile, each step itself already being two-dimensional, then we think of it as one big two-dimensional integral. It's not any harder to do the calculus, or at least not for this context, but that's what it is. And we call that final integral, that integral of dot products, we call that flux, electrostatic flux. And it's designated with a capital phi, the Greek letter phi. Okay, so this is a definition. We haven't done anything with it yet. It's not a law, it's just a definition, but now hopefully if like I've explained what the definition means, now we have to start applying it. Um uh I'm just seeing if there's anything else. Yeah, I guess quick. So I want to do an application now, and the first application I want to do is the beginning of that homework 7. Quick sidebar, quick. Um, like I'm like, again, I'm just really pleased that someone made the connection between work and this. That's a really good connection to make. For mathematical and physical reasons. And partly for not for many reasons. But one of them is to give you a sense of like why we even care about this. Like we just started getting into field, and field is a little bit abstract, perhaps. And now suddenly we're making it even more abstract by talking about field times area, flux. You might very reasonably ask like why do we care, or what's this for? And of course, the real answer to that question is you'll see. I mean, we have to use it in order to reveal its utility. But a little glimpse is we're following the same pattern that we did in early physics. It's the same pattern that brings us from concern for derivatives to concern for integrals. That is, remember, in the beginning of physics, uh, we think a lot about forces and accelerations. The whole idea is in classical mechanics is that if you know all the forces acting on a point of mass at a point of space in a point of time, if you know all the forces, if you draw the free body diagram, then F net equals ma, you then know the instantaneous acceleration of that point mass, and you can thereby predict where it will be when, or where it was when, right? But think about what that means. It means that the whole original picture of physics is know all the forces acting on a dot, know, therefore infer the acceleration at a dot of point in space, and from that dot, infer the rest of the movie through time and space, right? Acceleration is the second derivative of position with respect to time. So the whole original F net equals ma picture is super powerful. And in principle, it's all we need to do physics in a way, but it's a pixelated picture. The whole idea of it is if you scrutinize one frame fully, then you can infer the rest of the movie, right? It's dot by dot. Derivative, it's all about the limit as intervals of space and time approach zero. So that is super powerful and in a way super complete, but but it's in many cases very inconvenient to be looking at the world pixel by pixel. So then we shift our attention in in mechanical physics, and we say, okay, that's great, but also can we ever look at what is the accumulated effect of a force as it is distributed or acting throughout a finite region of space? And we call that an integral, right? We look at the continuous sum of products of the force times the dx, and we call that work, as someone in the class anticipated or realized. So work is the integral, the path integral of force throughout some one-dimensional region of space. And that allows, and by looking at work, at looking at the integral of force rather than looking at derivatives, we then start being able to zoom out and look at entire regions of space and time at once. And we come to conclusions about um, constant properties of these finite, large regions of space and time. Like we say, when you do work on an object throughout some space, you give it energy. And under various conditions, energy is this quantity that holds constant, even while other even while other measurements are changing, right? So by zooming out and moving from a derivative picture to an integral picture, we then discover certain measurements that remain constant no matter what. So we have all of a sudden all this analytical power to make predictions, to make ultimately the same types of predictions we always wanted to make, but now we can make them much more efficiently under situations where we have large regions of continuous activity of some kind or another, right? I'm trying to say, we moved from the derivative force picture to the integrated work picture in order to gain knowledge of constants and that much problem solving power. Similarly, here, the last few days we've been looking at field. How strong and in what direction is the field pointing at this point? What's the field doing at that point? What's the field doing at this point? Well, now, and that's all a derivative picture. Now we're going to say, wait, can we like look at the distributed accumulated effect of field throughout some slice, some swath of space? Can we integrate field throughout a space and call it flux? Yes, let's do that in the hopes that maybe by analyzing flux, we might discover some constants. Just like by analyzing work, we discover the constant known as conservation of energy. Okay, so it is a very similar type of thought process that we're going to embark on now. It is a little bit more abstract because now we're talking about field rather than force, and now we're talking about areas rather than lines. I mean, so it's more sophisticated, but it is the same concept or the similar. Okay, so now hopefully that helps a little bit. So now let's do an application. Um, okay. So here's the example. Oh, so, we'll see. Um, what I want you to picture is a point source, positive Q, like we've been talking about, a point source, like a proton, sitting there somewhere in the lab. And then you're going to imagine the space surrounding that point source. So you're going to imagine a sphere of radius r centered at the point source. And what we're going to compute, what I'm going to compute, is the flux, the electrostatic flux through the surface area of that sphere. So let's be careful before I dive into this. We're calculating, this is an example of calculating flux. It's our first example. Partly it's an example just to show you what it's like to calculate flux, but also because it produces a result that is important. But the thing to get used to right away is that we're computing flux through a certain area. Area means region of space. It doesn't mean material. So I'm asking you right from the get-go to picture the space surrounding a point source. I'm not saying that there's anything there at the space. I'm not saying that there's like a metal ball or a glass ball or anything. I'm just saying there's space. And if you picture the a sphere of space surrounding this point source, picture that the outer shell of that sphere is a surface. We're going to compute the flux, the number of field lines busting through that space. Okay, that's the goal of the problem. Last thing I want to warn you about before we do the problem is, so again, it's all about like how many field lines are flowing through an area. But notice, even right from the get-go, even in this first example, the area that I'm asking you to picture is a kind of interesting area. It's not, it is an area. I'm going to ask myself to compute the number of lines that are busting through the surface area of this imagined globe, but it is the number of lines busting through the area, like the surface area of the globe. That area is two-dimensional. All areas are two-dimensional, but it is in fact a surface area. It's technically what's not technically, it's what we would call in physics a closed area. Like it's not flat like this. It's warped and bends in on itself. We'll talk about that in more detail. Like, but that's still an area. In other words, areas can be open or be closed, just like lines can be open or they can be closed into a ring, right? But even if you measure the length around a ring, even if you call it a circumference and say that it is like 2 pi times some radius r, right? It's still 2 pi r. It's not 2 pi r squared. The length, like, right, what circumference is a length that is bent around some circle, right? It's still a length. It's a closed length, but it's a length. Similarly, with this surface area that we're looking at now, it is a closed surface area as opposed to an open one, but it is still an area. Okay. So we are going, so I'll just say this through the, right. Okay. Okay. So let's do the calculation. We have 17 minutes. Okay. compute the flux. Okay, we're going to compute the flux. So all the only way we can do it what is to apply the definition. The definition of flux is this. Okay, so I'm going to do this integral now. Well, okay. First of all, recall this is all like. Oh, okay. First, I'll draw the field lines. Like the field lines from this point source. We've said this. We said this Monday. The field line picture of uh from the due to the point source. What is it? Sorry. Okay, the field lines. They go on forever, right? They make this pattern because it's a point source. It's the pattern that we talked about Monday. Those are the field lines. Those are representative field lines. So what we're trying to figure out here mathematically is not what is the field at any given one point. It's what's the accumulated effect. In effect, we're asking what's the total number of lines that pass through this area that we're looking at. Okay. Now, how do we even know? Like we're looking at, so what's the field magnitude times this whole area is really what we're trying to figure out. Well, how do we even know anything about the field magnitude? Well, it's all based on Coulomb's law. Um, right. In other words, it's all based on this. Right. So I'll plug that into the integral. Okay. Or two. Right. So I'm plugging that into the integral. It looks like a hard integral to do. Let's just go one step at a time. First of all, 1 and 4 and pi and epsilon naught and q, those are all constants with respect. I mean, the variable of integration, sorry, the variable of integration is ds, is s, meaning surface, right? In other words, when we vary, we're walking from tile to tile, imaginary tile to tile around the surface of that globe. And at each tile, we're asking what's the field doing right here at this tile. So most of the factors in that field function don't change at all from tile to tile to tile, like 4 and pi and epsilon. So most of those things can be taken right out of the integral. So this isn't as bad as it looks. Now I'm going to leave the 1 over r squared for the moment, even though it turns out even that's not as bad as it looks. But let's talk about the vectors for a second, the vector symbols and the dot product and all that. Dot product means one vector magnitude times the other vector magnitude times the cosine of the angle between them, right? So let's do that. Right? It means you stand at each tile on the surface area of this globe and you ask, okay, sorry. Right. Um, then you ask, what's the magnitude of one vector times the magnitude of the other vector, and what's the cosine of the angle between them? Well, the first vector is r hat. That meant r hat meant the vector that points from the point, like point source, to wherever you're standing, wherever you're measuring the field, right? In other words, right? R hat is the direction from the point source to wherever you're standing. R hat is the unit vector that points from the point source, the charge, to wherever you're standing. R hat is the unit vector. So the size of it necessarily always is one. The magnitude of the unit vector is one, always. So that's not so bad. It's one, okay, times ds. ds, I don't know what that is. Yeah, I mean, that's the variable of integration. I'm not going to mess with that. But then times the cosine of the angle between them. The co between them. What does that mean? Them means the little bit of area that you're standing on, wherever you're standing on the surface area of this globe. Like cosine of theta means the angle between, well, let's see if I can draw it. It means there's a little bit of area that you're standing on, or over here would be a little bit like a tile that you're standing on, right? And the angle would be the angle between the norm to that area versus the r vector that's coming from the point source to where you're standing. Now, if you're following what I'm saying, it's a little bit hard for me to draw. Well, here, look over here. I don't want to mess up the, look over there. The blue arrow is the arrow of R. The red arrow is it would be an arrow that's pointing norm to the area that you're standing on if you're standing on the surface of the area of this globe. So if you're thinking that they're necessarily parallel to each other, you're right. If you're thinking, in other words, no matter where you're standing on this globe, no matter where you're standing, you are necessarily standing perpendicularly, like the area of this globe, no matter which piece of it you pick, the area of the globe, of a piece, a tile on the surface area of this globe is necessarily, definitely, always perpendicular to the radius of the globe, i.e., to the field lines coming out from the center of the globe, right? It's just like saying when you're standing on the earth, the floor of the earth is definitely perpendicular to the line of gravity. Like that's like horizontal is perpendicular to vertical. That is actually that was a bad way to put it, but that's the case, right? I mean, it's one of these things that's once you see it, it's so fundamental that I'm not quite sure I can break it down any further. But the field lines are definitely everywhere perpendicular to the surface of this sphere. That's what I'm trying to say. Therefore, no matter what, and that's, by the way, that's why we're starting with a sphere. It's not a coincidence. Um, so I'm saying that cosine theta, no matter what, everywhere is one. the norm and the field line are definitely parallel everywhere, which means the field line is fully perpendicular to the area everywhere. So this is full-bodied flux. So now the integral is getting a lot easier. Like all the vector issues are gone now. We just have the integral of 1 over r squared 1 ds. Okay. But what's the deal with r squared? Well, r squared is, again, is the length, is the radius, is the length from the point source to the edge of the globe. That is a variable in life. That's a variable. Like, yes, you could be farther, your globe could be bigger, it could be small. You could have weak field or you could have strong field. But it's not varying with respect to ds, right? Like the variable of integration, what we're doing is walking around from tile to tile on the surface area of this globe. No matter where we walk on the surface area of this globe, we're not changing the size of the globe. We're not walking to different surfaces. We're walking around a surface, if that makes sense. So, in other words, even r squared, I'm not, even though it is a variable, it doesn't vary with respect to the integration variable. Right? So the integral becomes so the r squared comes out. The 1 over r squared comes out of the integral. So we now have this is the whole integral now. It's just the integral of ds, okay? It's just the integral of ds. Now, even that, you might say, well, I don't know what the integral of ds is. Well, yes, you do, though. Like, what is the, if you, in math, if you just have the integral of dx, I don't care what x stands for. I don't care what x is measuring. If you have the integral of dx, uh, what does that equal? And I guess I am asked. Am I asking? Yeah, I'm at. If anybody wants to put in the chat, like, what's the integral of dx? We have 5 minutes. I think I can get. Oh, thank you. Oh my God, and that's awesome. Oh, and that was two of you. Thank you. And one of you, I want to say thank you, both of you. And you're correct, both of you. And one of you, I really appreciate because you like. Because you talk very selectively, and I appreciate that you're very careful about when you say stuff. And oh, and good. And another person who is selective and careful about what they say. And yes, you're anticipating my next question. Okay, so yes, very good. I'm saying that in general in calculus, the integral of dx is x, and ha! All right, fair enough. You don't know how to enter. Okay, fine, fine, fine. All right, but now since I'm rabbit holing myself since we only have 4 minutes, here's the deal: the integral of dx, whatever x stands for, is x, and that's not just a memorizer, right? What it means is when you do integral of dx, you're adding up all the little infinitesimal bits of x, whatever x is. So the total of all of them is x. Well, similarly here, as somebody has already pointed out in the chat, if we're integrating up all of the little ds's, I mean, that means we're adding up all the little bits of surface. What you get at the end of the day is the total surface. So yes, the answer to this integral is S. I know we have 3 minutes left, right? Is capital S, meaning, meaning the total surface area of what? Of that globe that we're walking around, the total surface area of a globe. And what is this? I'm not, well, you can put this in the chat if you want, but this is the surface area of a sphere. You did know it at one point in your life. Like you learned it in geometry. You might have forgotten it. That's fine. But I'm here to refresh your recollection and tell you that it's like going to be important in our lives again. The surface area of a sphere, with 2 minutes left, and we're just about done. I'll tell you this: you do know it. First of all, it's area, so it's got to be something like r squared or something like that, right? I mean, it's got to be a squared thing if it's area, and it's based on a sphere, so pi is involved, right? So it's like some kind of pi r. So like the volume of a sphere is 4/3 pi r cubed, right? The surface area of a sphere is 4 pi r squared. And if you see a connection between those two formulas now that you might never have seen before, you're onto something. The volume of a sphere is 4/3 pi r cubed. The surface area of a sphere is 4 pi r squared. We've got 2 minutes left. So, but I'm going to plug, whether you remember that or not, it's true. So I'm plugging it, but that's the total surface area of this sphere. So I'm plugging it in and look at this. Oh, 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 oh. I'm saying the answer, and this is the answer. I'm going to spend all of next week like talking about it and what it means, but the answer is this is the answer that the flux is a really simple answer after all of this work. And this is why we care about flux. It's just like with energy, like you do all this stuff and then like you get these simple things like energy conservation. The flux is Q over a constant. With 1 minute left, what I'm saying is the flux, the total amount of flux doesn't depend on R at all. If you make a really big sphere, if you make a really big sphere, you've got really big area, but you've got weak field going through that area because you're really far away, right? And if you make a small sphere, you've got really small area, but you're really close. You got strong field. And the two effects perfectly cancel out because the field gets weaker and weaker at the same rate as a sphere gets larger and larger, and that rate is r squared. You see what I'm saying? So the flux is a constant through a sphere, regardless of how large the sphere is. And that's like a big of a hint. I mean, first of all, that's an answer to something in the homework. But second of all, that's a hint as to why we care about flux. But okay, you've been very patient and very insightful. You keep doing what you're doing. I'll keep doing what I'm doing, and I'll see you Monday.